this video, we're going to talk about quantum tunneling. We will explain what quantum tunneling is, we will introduce the Schrödinger equation and the uncertainty principle, and we will explore real-life phenomena of quantum tunneling.
If we take a ball at the bottom of a hill, it needs to have enough kinetic energy to go over the potential energy of the hill so it can, just roll down the other side. Now, if we take a quantum particle, like an electron, as that goes towards a potential barrier with higher energy than the kinetic energy of the particle, normally it would just bounce back, but there's a small probability that it will just pass through the other side. And this is called quantum tunneling.
If we want to know the probability of finding this particle in a certain position, we use quantum mechanics. The time-independent Schrödinger equation is useful for this. The equation utilizes the wave function. The wave function describes the probability of finding a particle in its quantum states as a function of position, momentum, and time. By solving it, for the case where the energy of the particle is lower than the potential energy of the barrier, we find that there is a non-zero solution to the wave function on the other side of the barrier. In other words, the particle has tunneled to the other side. When passing through the barrier, the wave function behaves as a wave. The wave on the other side of the barrier is called an evanescent wave. Now we're going to explore the connections between Heisenberg's uncertainty principle and quantum tunneling. The uncertainty principle states that the position and momentum of a particle cannot be exactly measured at the same time with full precision. Mathematically, it can be described as follows. This principle allows the probabilistic particle behavior that's required for the particle to be found on the other side of the barrier. The uncertainty principle can be derived from the wave functions, and therefore explains the wave packet model of a particle. This is the idea that the particle is a wave packet composed of many waves. The probability of tunneling is a result of the superposition, or adding, of each individual wave function that composes the wave packet.
So far, this has all been about particles of the smallest order. So how about a more, real-world, repeatable example? Well, let's say we have a beam of light and a prism. If we take the beam and we move its incident angle around, we can find the critical angle where total internal reflection occurs. And the first thing about this is that we'll have evanescent waves, but more like wave disturbances, and you won't really see them, but they do propagate past the boundary, and they are constantly exponentially dissipating outside of that boundary. But what if you had a second parallel prism, and we move it closer and closer to the first prism until they're practically touching but not quite? Well, at some point the internal reflection ceases, despite there still being that small amount of air between the prisms. Now how does this happen? Well, the photons are effectively tunneling over the boundary and therefore being allowed to propagate as if it's still one medium. And this is known as frustrated total internal reflection, a simple, tried-at-home example you can use to understand this in a more visual way. Another use of the quantum tunneling phenomenon is in solar fusion. So, to go back to our opening section where you saw how challenging defeating a potential to get to the other side can be, the Coulomb barrier within a nucleus, aka the electrostatic repulsion between two atomic nuclei as they repel, becomes the hill that you're trying to get over. So just as with the photons, protons can tunnel through this barrier and reach the attractive nuclear well, despite not really having the thermokinetic energy needed to bypass the barrier classically. Thing is, the process is very much the same, other than the particles being a little bit bigger and still displaying wave behaviors.
So, let's conclude our quantum tunneling video. By the end of this video, you should know what quantum tunneling is, how to relate the time-independent Schrödinger equation and the wave function to the probability of finding the particle on the other side of the barrier, know what evanescent wave is, know how to relate the uncertainty principle to quantum tunneling, and you should know how to use quantum tunneling to explain frustrated total internal reflection and nuclear fusion. Thank you for watching from Group 61.